In today's lecture, we are going to discuss about a very important distribution which we name as the Poisson distribution. The Poisson distribution actually arises in a lot of instances, and what we are going to look today is the main learning objective for today's session is the first is we will derive the formula for the probability mass function by motivating it through an example. Then we look at the expectation and the variance of the Poisson distribution, and finally we look at a few instances or situations that can be modeled as Poisson distribution. So, what is the Poisson distribution? Many a time we are interested in knowing about the number of events that occur either in a fixed interval of time or space. What do we mean by a fixed interval of time or space? For example, we are interested in knowing the number of people who use a particular ATM in an hour, or number of vehicles passing through an intersection in a period of time, or number of typographical errors or mistakes, spelling mistakes in a page or in a book. So, you can see that when I talk about a page or a book, it is a space, whereas when I talk about an hour or a day or a minute, it is a time. So, many a time we are interested in knowing about the distribution of the number of events that happen either in an interval of time or space. And Poisson distribution is an appropriate distribution or is the distribution to model in these situations. So, the Poisson distribution is actually, when we know that these events happen with a particular average rate, let me call that average rate as lambda. I am just denoting this average rate by lambda. I also have an important assumption that these events happen independently of the time since the last event. What do I mean by it is, suppose I have different intervals. These are non-overlapping intervals. I have a number of events happening in this interval. I have number of events happening in this interval. These are non-overlapping intervals, and the events that happen with the known average, the events happening in this interval is independent of the events happening in this interval. That is what is the main assumption that we have. So, we tell that this x, and that is the random variable we are interested in, which is the number of times this event occurs in this interval. This interval again could be an interval of time or it could be an interval of space. We are going to model this as a Poisson with the parameter lambda, where this lambda is nothing but the average rate at which the event occurs. So, we call it that x is a random variable that follows a Poisson distribution with parameter lambda. The Poisson distribution also can be looked as an approximation of the binomial distribution. We have already learnt about the binomial distribution. If the probability of success is small and the number of trials is large, we will also look at this in greater detail during the course of the lecture. So, let us start with a particular motivating example to understand how the Poisson distribution arises in real world. Suppose I have a researcher who is actually observing the number of vehicles that pass a busy traffic intersection in a day. To understand about the distribution of the number of vehicles that pass through this intersection, what she does is she collects data on 1001 minute intervals. She looks at these 1000 1-minute intervals and notices or collects data on how many vehicles pass in each 1-minute interval. So, she tabulates the data and summarizes the data in a tabular form as given in the table. How I can understand this table is, there are 80 1-minute intervals where no vehicles pass. There were 225 1-minute intervals where one vehicle passed, and so forth. And there were 30 1-minute intervals which had more than 6 vehicles passing. I can also plot the bar graph, as we have seen that this bar graph is a good way of graphically summarizing this data, and you can see that the most number of vehicles which pass through a 1-minute interval is somewhere around 2 with a probability or relative frequency of 0.260, and you can see that this is how the distribution is given to us. we go further and we can look at the frequency tabulation along with the relative frequency. So 0, the value x, which is the number of vehicles passing through this 1 minute interval, can take value 0, 1, 2, 3 and greater than 6. With frequencies 80, 225, so forth to 30, I find out what is the relative frequency. Once I know the relative frequency, I know I can compute the average or mean by summing up this x into FR. What is x into FR? X takes the value 0, the relative frequency is 0.08. I multiply this column with this column, I get 0. 1 into 0.225, I get a 0.225. 2 into 0.26, I get a 0.52 and so forth. I find out this, I add this column up to get 2.39 and this 2.39 figures here. This 2.39 is the average or the mean number of vehicles that pass through this intersection in a 1 minute interval. Similarly, I can compute the variance by using the same relative frequency notion. I compute FRX square minus mean square. So, the summation of FRX square is 7.88 minus 2.39 square is 2.16 and this gives me the variance of the number of vehicles. What we observe here is the mean and variance are almost close to each other. That is one observation which we make from this. The other observation we see is the intervals are actually, they were independent. The number of vehicles that were passing are random and are independent of each other. The mean number of vehicles per minute is about 2.39. This 2.39 per minute is equivalent to about 143 per hour. This is telling me what is the average rate at which the vehicles pass through the particular intersection. Now, so the question that we are asking is there any appropriate probability distribution to model these number of vehicles at a traffic distribution? The answer is yes, and this count, again remember when we talk about a discrete random variable, we are interested in modeling a count. The count here is the number, I am counting the number of vehicles or number of typographical errors or the number of mistakes, number of people. So, when I am counting this in this interval of time, it will follow a discrete distribution and that distribution is what we refer to as a Poisson distribution. So, now let us look at how this Poisson distribution is derived. Suppose I have an interval, I am looking at it as an interval of time and I say that x follows a Poisson distribution with a parameter lambda. What do we mean by this? We are assuming the following, that the number of, I have intervals, the number of events occurring, first of all, I have non-overlapping intervals and the number of events occurring in these non-overlapping intervals are independent. Now, I am also going to assume the following, the probability of exactly one event happening in a short interval of time. Let me assume that the interval of time is short. The length of this interval is delta t. If lambda occurs per unit interval, then lambda into delta t, that is the probability of this event happening, and probability of exactly 2 or more events happening in the short interval is essentially 0. These are the main assumptions I am having. So, how do I derive the probability mass function for the Poisson interval with these assumptions? So, I want to know what is the probability of n events happening in this interval of length t. That is the question of interest. So, let us go and look at it. So, now I am going to define success as exactly one event happening in the short interval of length delta t. If exactly one interval happens, that is how I am defining success, and failure is no event happens or more than 2 events happen, and that I have taken it as, that is what I am defining. I know that the success happening and the probability of 2 or more events happening, exactly 2 or more events happening is 0. So, I am defining success as the probability of exactly one event happening. Now, if I am going to look at this unit interval and I am going to look at the length of this unit interval as 1 by n, 2 by n, k by n, so far. So, I am dividing this. So, I know that lambda is the average number of events happening in this unit interval. So, I can say that lambda into 1 by n is the probability with which exactly one event happens, because I have looked at my assumption and I said probability of exactly one event happening is lambda delta t. If delta t is 1 by n, lambda by n is the probability with which exactly one event happens, and this is nothing but the probability of my success. The probability of success, which is the probability of exactly one event happening in this small interval, is called probability of success, which is given by lambda by n. Now, the probability of, I can view now I have n intervals, and I know that the probability of exactly one event happening a probability of success in this interval is lambda by n, the probability of success in this interval is again lambda by n, the probability of success in this interval is lambda by n. Each one of them are identical. They are independent of each other, because that is again one of my assumptions. I can view the number of events happening in this entire unit interval to be a binomial with parameter n and p equal to lambda by n. So, once I view this as a binomial expression, then I can go back to my binomial probability mass function and see that the probability mass function, that is probability x equal to x in the binomial situation, is n, choose x, p to the x, 1 minus p to the n minus x. I can write it as n choose x, p is lambda by n to the power of x, and 1 minus lambda by n to the n minus x. Further, I can write this as n choose x, lambda by n to the power of x, 1 minus lambda by n to the power of n into 1 minus lambda by n to the power of minus x. I have just written this in as two terms, the product of two terms. So, you can see that if I do this change as writing it as n choose x, lambda to the power of x, 1 minus lambda to the power of n and 1 minus lambda to the power of x, this n choose x is further expanded as n into n minus 1 factorial into n minus x factorial, because I know n choose x is n factorial by n minus x factorial into x factorial. N by n minus x factorial is what I have here in the numerator. Now, further, I see that this term lambda to the power of x is independent of n and x factorial is independent of n. So, I remove these two terms, lambda to the power of x and x factorial. I retain this term here, which is n into n minus 1 into n minus x minus 1. This n to the power of x, I bring it here and I retain these as it is. So, I have a 1 minus lambda to the power of by n to the power of n and 1 minus lambda by n to the power of minus x. Now, let us look at this term in detail, the numerator of this term. I can write n into n minus 1 into n minus x plus 1 the following way. I can write it as n into 1 minus 1 by n into n into 1 minus 2 by n into n into 1 minus x minus 1 by n. This is how I can write the numerator here, and that is what I have written here. Now, this I have n into n into n into n x times. So, I get a n to the power of x. I already have a n to the power of x in the denominator. I can cancel out these two. So, I can see that this expression reduces to lambda to the power of x by x factorial into 1 by n up to 1 minus x minus 1 by n into 1 minus lambda by n to the power of n and 1 minus lambda by n to the power of minus x. This is what I have. Now, certain things which we want to notice here is this term lambda to the power of x by x factorial is independent of n. 1 minus lambda by n to the power of minus x as, so now I want to know what happens to this term as n tends to infinity. Now, n tends to infinity implies that my number of trials is really large. My number of trials is really large is also means that the number of intervals becomes really small. Let me reiterate. As my n increases, this means that my number of trials is going to be really large, and what happens is the number of intervals become really small, because as n increases, the length of the interval is going to become really small. So, what happens to this probability mass function as my n tends to infinity? So, we are interested in knowing what happens in the limiting case of the binomial as n tends to infinity. So, as n tends to infinity, I can write this n choose x, and I have simplified this n choose x as the following. So, I already have from my earlier slide, this is nothing but lambda to the power of x, n to the power of x. I can cancel out this n to the power of x. I have 1 minus lambda to the power of n by n and 1 minus lambda to the power of n by minus x. Now, let us look at these terms. As n tends to infinity, 1 by n tends to 0, x minus 1 by n tends to 0. So, you can see that this entire term in this bracket tends to 1 as n tends to infinity. Now, similarly, as n tends to infinity, this term tends to 0, and I have a 1 raised to minus x. So, this term also tends to 1 as n tends to infinity. Now, this term limit n tending to infinity, 1 minus lambda by n to the power of n is e to the power tends to e to the power of minus lambda. This comes from your calculus session. So, and this term lambda to the power of x by x factorial is independent of n. So, my entire limit as n tends to infinity is lambda to the power of x by x factorial into e to the power of minus lambda, as both these terms tends to 1. And this is what we have as the Poisson distribution, which is e to the power of minus lambda, lambda to the power of x by x factorial, and x takes the value 0, 1, 2 as n tends to infinity. So, it goes up to infinity. Another thing which you can notice is we said lambda by n equal to p. So, as lambda is kept constant, as n increases and p is very small. So, you know that the mean of a binomial distribution is n into p. So, we will revisit this very soon. So, now by getting this distribution, I can formally define that x, or the average number, if I have an average number of lambda events per interval, x is a Poisson distribution which captures the number of events in that interval, and the probability mass function is given by probability x equal to x e to the power of minus lambda, lambda to the power of x by x factorial. X goes from 1 to 3. So, this random variable x is representing the number of events. E, as you all know, is just the mathematical constant, which is usually 2.718. So, let us go back to our example here. This was the frequency which we observed, which was 80, 25, 260, 225, 110, 70 and 90. So, I saw the relative frequency was 0.08, 0.225, 0.260, 0.225, 0.110 and 0.07 and 0.03. You can see that the relative, and this probability is what we observe is e to the power of minus lambda, lambda to the power of x by x factorial. So, 0.092 is e to the power of minus lambda, lambda to the power of 0 by 0 factorial, where lambda is what I have looked at the average rate. I also computed the average rate, and that average rate is what we get from our earlier table, which was about 2.9. That was the average rate, 2.39. So, I put e to the power of minus 2.39. I can get, once I put e to the power of, so how did I get this 0.92 here, 0.092 here? We just substituted the value. So, I get e to the power of minus 0. E to the power of minus 2.39, 2.39 to the power of, I set e to the power of minus 2.39, 2.39 to the power of 0 by 0 factorial, that would give me a 0.092, e to the power of minus 2.39, 2.39 to the power of 1 by 1 factorial will give me 0.219, and so forth. It will work out for everything that we have kept here. This is greater than 6. So what we see is, I started by asking the question that, okay, I have performed an experiment where I observe that this is my frequency distribution, and the frequency distribution gave me a particular mean. So I started with the question that, is there an appropriate probability distribution? And now I got the answer, yes, there is an appropriate probability distribution, and that distribution is what we refer to as the Poisson distribution. So you can see that the Poisson distribution with lambda equal to 2.39 gives us precisely or very closely the values that we got from our observed distribution. You can see that the bar chart, which are blue bars, is what we saw was from our observed distribution, and the red is what we get from our fitted or from the probability Poisson distribution. And you can see that they have almost the similar distribution pattern. So now we are convinced that Poisson is a good distribution when it comes to model such events when I have over an interval of time. So the next question is, how does the shape of the probability mass function change with respect to lambda? Because we see that the probability mass function is e to the minus lambda, lambda to x, x factorial. So the only parameter that defines it here is e to the minus, it is lambda. So this lambda e remains constant, and for every x, this lambda is the only thing which is a parameter. So if lambda is small, so let's look at how does the distribution or how does the probability mass function look for lambda equal to 1. So when lambda equal to 1, you see that as x tends greater than 5, you can see that it is almost going to 0 with the probability being really high. So it is e to the minus lambda, which is 1, into lambda to the power of x by x factorial is just going to be 1 by e, because lambda is always 1. This will give me 1, this is going to be 1 factorial for any x, this is going to be 1, so it's just 1 by e. So you can see that it almost has a structure of 1 by e. So for small values of lambda, you see that this distribution has a positive skew. What happens as lambda increases? For example, when lambda equal to 4, I get e to the minus 4, 4 to the x by 4 factorial. You see that the distribution is changing. Eventually, what happens when lambda equal to 8? You can see it becomes symmetric. Now, again recall, when I had a lambda, I defined lambda by n equal to p. When lambda equal to 1, I have p equal to 1 by n. As n increases, this p becomes really small, and when p is really small, we had positively skewed when we looked in our binomial distribution. Similarly, when lambda equal to 4, my p equal to 4 by n, and when lambda equal to, so here when it is, I have taken n equal to 16, this becomes 1 by 16, this is going to be 1 by 4. When lambda equal to 8, my p equal to 8 by 16, which is 1 by 2. When p equal to half, we have already seen that we will get a symmetric distribution. So you can see that as lambda is, when lambda is very small, I have a positively skewed distribution, and as lambda increases, the distribution becomes progressively more symmetrical. Okay. So what we have learnt in this section is, we have introduced the Poisson distribution, the Poisson random variable, which counts the number of events happening in an interval. The interval could be an interval of time or interval of space. We define the Poisson distribution with a parameter lambda to be the probability mass function is e to the minus lambda raised to x by x factorial. We also saw the shape of this distribution.